Everyone, my name is Martin Moro, and with this video, I just wanted to briefly summarize one of the topics covered at the EuCAPT school. This topic was covered by David Wons, and other topics that happened at the school were primordial black holes or modified gravity, for example, among others. But I just wanted to focus on this topic that was given by David Wons. So, uh, first, I just wanted to mention a bit what we know about cosmology, and it's basically the model that we had about the hot Big Bang. And from this model, we can infer how the first stars were formed and then how the first galaxies were formed. And with this model was really supported by the discovery and the observation of the CMB, as we all know. But it has two main problems that what's motivated the inflation model. These two problems are the horizon problem and the flatness problem. So I said that the CMB was one of the biggest discoveries in cosmology and biggest observations, but from that we can infer that most parts of it had never been in casual contact before. So from this diagram we can see that the points P and Q were not in casual contact at the singularity, and that gives rise to the horizon problem. And the flatness problem comes with the fact that in the early universe any perturbation and any initial curvature would grow, and therefore we would not have a flat universe as we have nowadays. So the inflation model tries to explain these two problems and give an answer to it. And it's basically these two problems are basically explained with if we consider that there was much more time before recombination than we thought of. As we can see here, if we consider much more time before recombination and reheating, we can see that the points P and Q were in casual contact at one point in time. So what this model explains is that considering the evolution of a scalar field with a particle, as we know, as we consider the inflaton, and with the energy density V, these points would be in casual contact before, and these perturbations would not, this curvature would not grow that much, and we would give flat universe as we understand it nowadays. So the dynamics of during inflation and in this model are determined by these equations that we can see here, and then this model, the inflation model, is constructed with the slow roll approximation. And this slow roll approximation is basically stating that for inflation to persist, the acceleration must be really small. And therefore, as the inflationary energy decreases, we can see with the function, the kinetic energy would increase, and this field would oscillate with within this the minimum, and at that point the matter would start to dominate, and then the hot Big Bang, as we understand it, as we know it, would evolve and would start. So now that I explained a bit about the slow roll approximation, really briefly, we have to have some bounds and some constraints that here they were given by the Planck in 2018. So we can see different models of inflation. One considers, for example, the potential to be proportional to phi squared. Then another one proportional to phi to the 4 over 3. Another one considers the potential to be only proportional to phi. And all these ones are subjected to changes because there's not one model that defines completely inflation. But as we understand it, inflation must have occurred in order to address all the problems that I mentioned. And even though we don't have a specific model that explains completely inflation, we know that the idea of inflation and the primordial perturbations that gave rise to all the hot Big Bang, as we understand it, gave rise to the stars and galaxies as we can see, as we can infer from the CMB, must have occurred. So if you want to know more and understand more about this um, inflation model and the primordial perturbations, please, if you have the chance, do not hesitate to go to the EuCAPT school. It's really worth it, and I hope this video makes you want to learn and know more about inflation and cosmology.